so the next talk is about we're done with the negative talks. I guess. And we'd like to divide the talks shortcut conjecture. So this is a paper by Aaron Bernstein, Henry Fleischmann, Max Gutenberg, Bernard Hochler, Gary Hoffenborg, Jon Young, George Lee, Seth Betty, Sachaformat Saranorak, Leon Schiller, and Henry Fleischmann. Henry will be
Yeah, thank you. So today I'll be talking about our recent work on reviving Thorpe's shortcut conjecture. But first, let's take a trip to Manhattan. Okay, so the Uptown train in Manhattan is looking for an upgrade. It looks like just a directed path from downtown to uptown with some stops in between. And Manhattanites are angry because 8 stops from downtown to uptown is quite a lot for them. And so the train company, looking to avoid a riot, hires a network designer to suggest some new express lines. And the network designer suggests adding express lines like this, with the consequence being that if you add those express lines, now wherever you get on, you can get to where you wanted to go in just 2 stops. So motivated by Manhattan, I can define the notion of shortcut sets. George talked about this a little bit before. So given a directed graph, a shortcutting of the graph is just an augmentation of the graph. You add some extra edges such that you preserve reachability. For all S and T vertices in the original graph, S can reach T in G if and only if S can reach T in the shortcutted graph. So essentially, you're adding edges to maybe reduce the length of the shortest paths, but you need to preserve reachability. And I call E plus the shortcut set. So the same example from Manhattan, directed path, we can shortcut it to diameter 2 by adding shortcut edges, the express lines, as so. Let me just clarify one thing here. When I'm saying diameter 2, I mean specifically the maximum distance between S and T such that S can actually reach T. This is not the maximum distance between any pair of vertices in the graph, because I want this to be finite. Okay? And when we talk about shortcut sets, the interesting regime is when the size of the shortcut set is much smaller than n squared, because of course, if we allow n squared edges, we can just reduce the diameter to 1. Just add direct edges between all S and T where S can reach T. Good. So shortcut sets are interesting as a combinatorial problem in and of themselves, but another reason to care about shortcut sets is their application to a big open problem in fast graph algorithms, which is, can we solve ST reachability in parallel and in near linear work? Where in parallel we want like small depth, maybe polylog. And let me just say, you've probably seen ST reachability. This is just the problem of you have a graph in S and T, can S reach T? You can solve it in BFS, with a BFS sequentially. It's also the canonical NL complete problem. And we do have an algorithm for solving this in parallel. You can just take the adjacency matrix of the graph and repeatedly square it, log squared n rounds in parallel, and just polylog matrix multiplications will tell you if S can reach T. But the problem with that algorithm is the total work, the total number of operations over the parallel machines, is O tilde of n to the omega. The tilde is just saying I'm hiding log factors. That omega is the matrix multiplication constant, but in particular, it's at least 2. So this is not going to be near linear total work. Okay. So you can use shortcut sets to get algorithms for parallel reachability. So let's suppose you have a shortcut set, which is good in the sense that it reduces the diameter down to D, and the size is only O tilde of M. That M is the number of edges in the input graph. Then if such a shortcut set exists, you could hope to run the following algorithm. You compute such a good shortcut set, and then you take the shortcutted graph and run BFS on that graph starting from S. And you only run it for D rounds in parallel to check for a path from S to T. And the idea is, well, because of how we define shortcut sets to preserve reachability, S can reach T in G if and only if S can reach T in the shortcutted graph. And the shortcutted graph has diameter D, so you only need to do D steps of BFS. So that gives you the low number of rounds in parallel. And then the fact that you get near linear work is just coming from you're running BFS. So it takes the size of the shortcutted graph, which is O tilde of M. So you might think this is a bit too idealistic. That first step of computing the shortcut set is definitely a non-trivial task to do efficiently in parallel. And that's true. Nonetheless, this is actually the template for the state-of-the-art parallel reachability algorithms. And so this is one reason to care about shortcut sets. Okay, so motivated by this application, and some other things I'll say in a minute, in 1992, Thorup conjectured that all graphs admit good shortcut sets. Namely, there is a shortcut set of size O tilde of m such that it reduces the diameter all the way down to polylog n. And it's pretty easy to show this for trees, and he managed to show it for planar graphs, and in fact later it was extended to H-minor free graphs. And of course, as we saw, if this were true, you could maybe get good algorithms for parallel reachability. But unfortunately, it's false, and Hesse in 2003 gave a nice refutation. So Hesse showed that there's a family of graphs where these graphs have diameter n to the 1/17th, and any shortcutting which reduces the diameter, and I should say has size O tilde of m, or no, yeah, any graph that reduces the diameter has to have size at least m times n to the 1/17th, which is definitely not near linear. Okay, so by itself, this refutes Thorup's shortcut conjecture. And in the time since, there's been a series of strengthenings of lower bounds for shortcut sets. We've gone all the way from n to the 1/17th up to n to the 2/9 from Hoppenworth, Zhu, and Zhu in 2025. And in this table, for each reference, this is a family of graphs such that any shortcut set of size O tilde of m, which reduces the diameter, or any shortcut set of size O tilde of m can't reduce the diameter better than the bound on the right. Okay. So it's very natural to think at this point, the approach that I sketched for parallel reachability of compute a nice shortcutting of the graph and then just run BFS is dead. But to see whether that's like really the case, let's go back to Manhattan. So since we've been here, time has passed, and the network designer we had before has come and gone, and the Manhattanites are predictably mad once again. And so since we've last been here, there's a new train line. The Manhattanites mostly live downtown, and they work uptown. And there's 9 train lines going from 3 starting downtown terminals to the final 3 uptown terminals. And these train lines only intersect at the final terminals. And between them, they have these really long paths, a bajillion stops. And so they're upset because that's a bajillion stops to get to work. And because there's so many stops, it's too expensive to do the same solution as before, where we just shortcut all of the lines with express lines. So train company hires a new network designer, and they propose an interesting solution, which is you add a super hub. This is a new station where we connect all of the initial downtown hubs directly to the super hub, and then the super hub directly to the final uptown terminals. And if you do this, well, the commute is only 2 stops. So Manhattanites are sated once again. And so given this, we can define Steiner shortcut sets. So given a directed graph, a Steiner shortcutting is very similar to a shortcutting. It's just, instead of just adding extra edges, now we can add some extra vertices. And we want the same guarantee as before. For all pairs of vertices S and T from the original graph, we want that S can reach T in G if and only if S can reach T in the shortcutted graph G+. So this extra set of vertices is the Steiner vertices. So note that we just care about preserving reachability for the original vertices. The Steiner vertices are just there to help. Good. So same example we saw from Manhattan. It's just a biclique with subdivided edges. And one way to add a Steiner shortcut for this is add a Steiner point and connect the beginnings and ends of these subdivided edges to it. That's not shortcutting all of the nodes, the paths between all the nodes here, but it's an example of using a Steiner point. Good. So one reason these Steiner shortcuts are interesting is because they suffice for our application to parallel reachability. If you can compute a good Steiner shortcut set, then you can still do the same approach of just run BFS on that shortcutted graph. And why this is particularly interesting is our main contribution, which is all the known lower bounds break once you allow Steiner points. So we construct Steiner shortcuttings where the size of the shortcut set is O of m, and we reduce the diameter all the way down to log n over log n. So these were all the lower bound constructions, and none of those diameter lower bounds hold once we allow Steiner points. We have Steiner shortcut sets reducing the diameter to log n over log n. And so for the application to parallel reachability, we can revive Thorpe's shortcut conjecture. And in our work, we conjecture that all graphs admit good Steiner shortcuttings. So this is a Steiner shortcut where the size of the shortcut is O tilde of m, and we reduce the diameter down to log n over log n. Or sorry, polylog n. Good. Good. So we don't really know if this is true. But before our work, there are no lower bounds against Steiner shortcut sets. And another of our contributions is the first weak lower bound against shortcut sets, Steiner shortcut sets. And we show that Hesse's construction gives you some lower bound. So any Steiner shortcutting of Hesse's construction of size O tilde of m can only reduce the diameter down to log n over log n. And you might hope, okay, well, Hesse's construction seems pretty good. Maybe we can get an even better lower bound. But remember, our first contribution was actually we can construct a Steiner shortcut for this graph, this family of graphs. So this analysis is tight. So our next contribution is a candidate hard instance, which is if you take Hesse's construction and you inject noise, so you delete each edge with some carefully chosen probability, we show that that construction is strictly harder to shortcut with Steiner shortcuts than the original construction. So there is actually an explicit gap. Unfortunately, the gap we show isn't enough to get better asymptotic lower bounds. And we leave it as an open problem to either prove better asymptotic lower bounds there or actually construct a Steiner shortcutting. So let me conclude. So for the algorithmic application to parallel reachability, Thorpe's shortcut conjecture is still open. Those existing lower bounds can all be broken with the addition of Steiner points. We make this conjecture about Steiner shortcuts, and in starting to understand whether this might be true, we give a first lower bound and propose a candidate hard instance. Now, I want to say a few avenues for future work here, since this talk is mostly about conjectures. And one way to maybe make progress towards the Steiner shortcut conjecture is to take an alternative perspective based on circuits. So it turns out the shortcut conjecture is equivalent to a conjecture about depth reduction for OR circuits, which is kind of weird. So given a circuit on M wires where the circuit only has OR gates, the conjecture is there's an equivalent circuit on O tilde of M wires, so maybe some more wires, where the depth is only polylog M. It's not too hard to show this is equivalent, and it's interesting because once you adopt this perspective, there are some known results in the literature you can use to prove, give another proof of the log n over log n lower bound. But we don't really know how to use stronger results from, say, circuit complexity here. Okay. Secondly, we currently don't understand the power of Steiner points at all. Insofar as we don't really have good lower bounds. The only lower bound against Steiner shortcut sets is that log n over log n that we show. And all of the upper bound constructions for shortcut sets don't take advantage of the, or at least all the general constructions for shortcut sets don't take advantage of the strength of Steiner points. They just don't use them. So we don't know if there's maybe a better shortcutting algorithm which exploits Steiner points, and that's an interesting open problem. Okay, thanks for your attention. Happy to take questions. Yeah. No, it's okay. The way in which Steiner points break the lower bound constructions, which is really the only way we know how to use them, is the fact that if you imagine a biclique with the edges being subdivided into long paths, you can do that sort of shortcutting I showed, where you add one Steiner point, connect all the vertices on the ends of these subdivided biclique edges to the Steiner point, as opposed to adding direct edges between all the edges of the in the biclique. So that gives you like a quadratic savings. So we use that in order to break the lower bound constructions, but it's not really clear how to exploit that for upper bounds. Yeah. So mostly no. Yeah. No. Oh, well, okay. So there, like for graphs that embed into hypergrids, you can use Steiner points in an interesting way, I think. Otherwise, yeah, there's some special cases you can use Steiner points, but in general, like the best algorithms just don't use Steiner points. It's like this n to the 1/3 diameter construction, which is the best, doesn't use Steiner points. Yeah. Yeah. As in, like you didn't have to preserve all reachability relations, but maybe like some. Oh, I see. No, although it's likely that this is another object in network design. This Steiner version of shortcut sets is like the simplest version of many other related problems in network design, and you can introduce Steiner points here. You can introduce Steiner points in those other settings too. Many we don't really know anything for. And they also have interesting applications to parallel versions of other problems like single source shortest paths or max flow. But yeah, we really don't know very much.